Today we're going to learn Chapter 3, The Elements of Climate, a global view of pressure, winds, and storms. This chapter has 6 parts, so we'll go over each of the key points. We're going to examine the climatic elements, cheating air pressure, winds, air masses, frontal zones, storm tracks, thunderstorms, and mesoscale convective systems. These can be considered as the dynamic elements of the climate system. Pressure differences are the driving force for winds and storm tracks. Air mass contrasts give rise to frontal zones and to changing weather conditions. Thunderstorms may occur as single-cell or multi-cell clusters. Mesoscale systems are usually violent, moving storms, intermediate in size between thunderstorms and synoptic cyclones. The latter are low-pressure systems that are featured on a weather chart, with a diameter of 1,500 to 5,000 kilometers and a lifetime of 5 to 7 days. Atmospheric pressure is the force per unit area exerted on a surface by the weight of air above it. Pressure decreases with latitude as there is less overlying weight of air. Observations of pressure at a station made by measuring the height of a mercury column in a mercury barometer are reduced to measure at mean sea level. By corrections for the latitudinal variation of gravity and for air temperature. At MSL, the mercury column that is supported by the weight of the atmosphere is approximately 700 mm, around 29.9 inches tall. Atmospheric pressure at mean sea level averages about 1,030 millibars or 10,000 per hectopascals. The pascal unit of pressure equals a force of 1 Newton per square meter. So we use the traditional millibar unit here in this lecture. The record now, the record low value was 870 millibar in the eye of super typhoon Tip in the Northeast Pacific in October 1979. The highest recorded MSL, the mean sea level pressure was 1,083 millibar, measured at Agatar in northeastern Russia in December 1968. The daily or weekly change of pressure is recorded by a barograph. This is an ameroid barometer comprising an evacuated metal chamber that responds to air pressure changes. It is connected via a series of levels to a pin that traces the pressure on a chart attached to a rotating drum. The spatial pattern of pressure is largely zonal, with low values near the equator. The equatorial trough of low pressure flanked in each hemisphere by subtropical high pressure cells anticyclones, which are in turn flanked by superpolar low pressure. The subtropical anticyclones extended vertically throughout the troposphere and are present through the year. So in this image, we show the mean sea level pressure in the northern hemisphere and also in southern hemisphere both in January and July. The northern hemisphere anticyclones at the surface are known as the Azores high pressure and the North Pacific high. Left image, the southern hemisphere anticyclones are correspondingly located in the Southeast Pacific, the Southeast Indian Ocean, and the Southeast Atlantic Ocean. In winter, the northern hemisphere, there is also as pronounced but shallow high-pressure cell over northeastern Siberia related to cold, dense air. The high-pressure cell shift very little on a day-to-day basis. The subpolar lows in the northern hemisphere are located near Iceland and the Aleutian in winter, while in summer the former weakens and the later disappears. So it's this graph B. In the southern hemisphere, there is a more or less continuous subpolar low around Antarctica in both seasons. So we can see here, on a weekly timescale, low-pressure system cyclones move broadly eastward across the mid-latitude oceans and continents at about 20 to 30 kilometers per hour. For a mature low-pressure system in mid-latitudes, the central pressure is about 960 to 990 millibar. Lows form, deepen, and then decay. Anticyclones are larger in extent and much more static components of the weather map. In the subtropics, they may move only on a seasonal time scale. Their central pressure is typically around 1030 to 1040 millibar. In the troposphere and stratosphere, the geopotential height of a pressure surface has been used for convenience since 1946, rather than the pressure values at a constant height. The 500 millibar pressure surface is at a height of about 5.5 kilometers, 5,500 geopotential meters, or GPM. The geopotential height is given by an adjustment to geometric height above mean sea level, using the variation of gravity with latitude and elevation. Geopotential and geometric height are numerically almost equal. Pressure decreases exponentially with altitude, whereas temperatures decrease nearly linearly. Hence, the pressure is about 1,000 millibar at sea level, 500 millibar at 5.5 kilometers, and 100 millibar at 15.5 kilometers, and 25 millibar at 25 kilometers. The upward pressure gradient in the atmosphere is counterbalanced by downward gravitational acceleration. This gives rise to a state of hydrostatic equilibrium. Winds. Air motions is given its initial impulse by horizontal pressure differences that result from contrast in heating and air density. The wind flows towards lower pressure to transfer mass. Wind velocity is a vector quantity comprising the wind direction. 360 degrees is a north wind, 90 degrees an east wind, and so on. So 360 is the north, and east wind is 90, and this will be 180 and 270, referring to the direction from which the wind is blowing. And the wind speed is a standard height of 10 meters above the ground. Average over a minute or so. Wind speed Wind speed is measured using an anemometer. Anemos is Greek for wind. The anemometer is invented in 1848 by J.T.R. Robinson at Armagh Observatory in Ireland. It consisted of four hemispheric cups mounted on a rotating vertical spindle. Modern versions have three conical cups set at 120 degrees apart. Nowadays, sonic and anemometers, which measures ultrasound waves, invented in the 1950s, are often used, especially on automatic weather stations. Direction is measured by a wind vane to tenths of degrees. Speeds are measured in meters per second. The distance the air moves in 1 second at some locations. A continuous record of wind speed and direction is obtained with a pressure to amyograph, which records wind speed at a pitot device. Gale force winds have speeds greater than 17 meters per second. Gusts are defined by a brief, less than 20 seconds increases of speed exceeding 8 meters per second. The world record gust is 113 meters per second, is like 253 miles per hour. Measured in a tropical cyclone of Western Australia. Squalls are like gusts, but typically lasting longer than 2 minutes. Above the surface, winds are determined by radar tracking of helium-filled sounding balloons called wing sonates. Radar wing sonates. So look here. Such soundings are made 1 or twice per day at about 700 stations around the world. Wind data are sometimes displayed on a wind rose, which shows the frequency of winds from each direction and their speed distribution in a polar coordinate plot. An example for LaGuardia, New York in 2008 is shown here in this slide. This enables the most frequent wind directions to be easily seen. The resultant wind is the vector average of all directions and the speeds. The mean wind speed is average for a day or month for all wind directions and calm conditions. In general circulation studies, it is common to determine zonal westerlies and meridional southerlies components of the wind. Easterly winds are negative westerlies and north winds are negative V. The surface winds are basically recognized in two extensive systems in each hemisphere: the tropical easterly trade winds and the mid-latitudes westerly winds. The trade winds are highly constant in direction, whereas the westerlies are much more variable in direction and in speed, especially in the northern hemispheres. As a result of the presence of the land masses, the winds above the friction year 1,000 meters deep below parallel to the isobars lines of equal pressure with low pressure on the left, right in the northern southern hemisphere. This is known as Bias-Ballot's law.